obviously at this point, I don't know how to do that any other. So, thus always a long pause in the first 5 seconds. So this chapter is a lot more straightforward than the last chapter. I know you're probably looking at the word going, really? That's a lot more straightforward to me. Well, most of this is going to be for the second part. This is going to be a 2-parter, maybe 3, depending on how long they go. Last time we did electrostatics. Today we're going to look at circuits. So our goal is to understand electric circuits. Our objectives are to understand the flow of charge and how that leads to circuits. We're going to understand voltage and what it is, and what it means, and how to calculate it. We're going to look at Ohm's Law. We're going to learn about shocks and whether a shock will kill you or not. We'll compare alternating current to direct current in the second part. We'll learn about motions of electrons, understand power. Actually, power will be in the first part. And then we'll take a look at, actually not the first part. The second part will be about different types of circuits, in series, in parallel. Then we'll learn about fuses and transformers. But unlike the Hollywood transformers, the physics transformers are all that meets the eye. In fact, it'll be one of those straightforward things in the entire semester. So, flow of charge. About 200 years ago, Benjamin Franklin proposed that the current was the flow of positive charges and the negative charges stayed put. But he got it backwards. We now know it's the electrons that move, the positive charges that stay put. So charge flows from high potential to low potential, and this is similar how water travels. So a circuit is kind of like a flow of water from point A and around and back to point A again. So it's like a closed loop, if you will. A water slide, if you will. And the charges go to a high potential and then they flow back down to the low potential again. And then the process repeats. It's kind of like the game Chutes and Ladders, except the physics versions of it is the most boring, one of the worst board games ever made because you always end up right where you started. So I guess it's not that far different from the real Chutes and Ladders. Voltage. Voltage is a measure of electric height. So 8 volts means that you're 8 volts above the ground. So if you have a battery acts like a pump, a fountain if you will, and it shoots the charge up to a height of 8 volts. And then that charge has to come back down the 8 volts to get back down to ground again before the battery can move it back up again. And it's that flow up and then back down that is the essence of the circuit. This is very similar to water. I take a pump, I pump the water up, I put it into a tube, the tube goes down to the bottom, to the ground, if you will. That's the big pool at the bottom of the water slide, and then I pump the water back up again. Now, in the case of the water, if you're looking at the Earth, the energy source of the battery, if you will, is the sun. That's the hydrological cycle. If you're at a water slide, then it's electric pump issue battery. But batteries act the same way. Batteries are pumps for electric charges. They push them up to a high voltage, and then they come back down again. So voltage is just a measure of your electric height. Now, resistors allow you to resist the flow of charge. They limit the speed of charge, of how quickly the charges can move around in your circuit. This limits the current. The current is defined to be the amount of charge that passes by a part of your circuit in a given amount of time. So the speed at which the charges move is affected by resistance. So your faucet is an example of a resistor for water. It resists the flow of water. The more you have the faucet on, the more water that can flow through. You can turn it completely off, giving it, in essence, an infinite resistance. There's no flow. If your faucet breaks so that your resistance goes from infinite to really high but finite, then you'll get a drift, and that'll annoy. So non and infinite resistances for faucets are annoying. I know, we physicists make the worst plumbers. I see a problem. Your resistance is not infinite. You need to turn your resistance to infinity. Great, how do I do that? I don't know, I'm a physicist, not a plumber. All right, so suppose we went the other direction. Suppose we bought a faucet that could be turned on to a point where it had zero resistance, no resistance at all. Kind of like a circuit without resistance. What would happen to my sink in my kitchen if I were to turn that faucet on for 1 second? So I want you to ponder that for a moment. What would happen to my kitchen if I turn on a resistanceless faucet for 1 second? What would I get? Are they, well, I get quite a bit of water or maybe a little bit of flooding. I'd probably have to get out the mop. Well, I don't think a mop's quite going to help you, because this would be the result. But a minute, you always wanted a kitchen like this. Okay, maybe not. Without any resistance, you would have infinite current. Infinite current. That's why when you build a circuit in your labs, in lab part of class, or anywhere, always make sure you have some resistance in your circuit. Otherwise, you end up with infinite current, which heats up the wire and basically burns your house down. This is called a short. Shorts are very bad. People die because of this. So make sure you always have resistance in your circuit, otherwise you'll toast your devices that you're using in lab, and they are not easy to fix. Not easy at all. And I don't even have to fix them. I know they're not easy to fix. So always have resistance. Now, this is what a resistor looks like, at least the ones you play with in your circuits. These bands tell you how much resistance is in that particular resistor. It's a coding, if you will. But the actual value of the resistor depends on a couple things. Now, the following is a little bit more advanced, and we won't use it in our class a whole lot. This is more for trig-based classes. I'm just showing it to you for completeness. So the resistance of a resistor equals a constant for the material you're using. Some materials have a very high constant, some materials have a very low constant. We talked about conductors versus insulators. A conductor would have an extremely low value for that rear-looking P. An insulator would have a very high value for that rear-looking P. Most resistors are made of ceramic, which have a pretty moderate value for that. And then you multiply by the length of the resistor. The longer the resistor is, the harder it is to complete. Kind of like if you have an obstacle course, the longer the obstacle course is, the harder it is to complete. Therefore, it has a higher resistance. The difficulty of the obstacles would be the value of P. So if you had no obstacles, it's like a wire, it's very low resistance. But again, the longer the race, the higher the resistance. So, if you have to run 100 meters, not so bad. If you now have to run 3,200 meters, 2 miles, well, you'd probably look at me funny. Unless you did track in high school, like I did. Divided by the area, cross-sectional area. The bigger the cross-sectional area, the easier it is for charges to flow. Much like if I have a big pipe, it's a lot easier for water to flow. If I have a little pipe, it's very easy for that pipe to get clogged. And so the flow is slow. In fact, that's how we adjust the resistance of the faucet, is by opening the size of that hole. There is some dependence on temperature if you're doing higher level things, but that dependence is very small, and unless you change the temperature by quite a bit. So in this class, even in trig-based classes, you ignore the temperature dependence. And in a calculus-based class, most of the time you're probably going to neglect it anyways. So I just do want to mention that there is a slight dependence on temperature. But most of the resistivity depends on the substance and the dimensions of the substance. Now in this class we'll have a resistor with some given resistance, or we'll calculate the resistance based on other things. We won't use that particular equation. In fact, you notice I didn't even write that equation before, so it shows you how much you're going to use. This leads us to Ohm's Law. So we have a resistor with some amount of resistance. And we have a voltage based on the battery. Now the question is, how much current are we going to have going through that circuit? Well, the voltage equals the current times the resistance. Please note that the symbol for current is I, not C. This is really confusing, but in Italian it's inductore. It starts with an I, and that's why the physics symbol for it is I. Voltage is V, resistance is R. Voltage is in terms of volts. Current is in terms of amps, and resistance is in terms of ohms. So that means that voltage divided by current is futile. Not a Star Trek fan? Okay. So going back to the water analogy, how fast the water moves depends upon how high up you move it and how big the barriers are on the way down. If it's pretty smooth, it'll flow down very quickly. If it's very rough, it'll flow down much more slowly. Electrocution. All right, so let's examine what it takes to kill a person with electricity. So 2 questions before we get to the amount and which of those 3 values, voltage, current, or resistance, is the culprit. Suppose that you had a friend who was being electrocuted. How would you be able to tell? And if you figured out that they were being electrocuted, how could you end the electrocution so that they don't die without putting yourself in harm's way? That's the thing. All right, so ponder those for a moment. As I go and touch a wire. All right. I'm about to do this for science. Do not attempt this at home. I'm what we call non-professional. Ah! Okay, clearly that was fake. Why? Because if you're truly being electrocuted, you can't make sounds. Your voice box is not going to work right. So if someone's screaming, that means they're faking it. They would just kind of twitch a little. So that's how you can tell. How do you end their electrocution so that they don't die? Well, don't grab them, because you will also become electrocuted. You want to do something so that you will not become part of the circuit. That means you need to put a whole bunch of resistance between you and the other person. You could throw something at them and hope that it knocks the wire away from their hand or knocks them off the wire. That way you're not touching the item that's touching them, because if you're touching the item that's touching them, you'll be part of the circuit also. Or you use something that would not conduct electricity, such as wood, or plastic is usually a pretty good insulator too. So you can take a wooden chair and push them with a wooden chair or with a baseball bat. Don't hit them with the baseball bat. That might cause other problems. But something like that, and get them off of the circuit and hopefully they can survive. But the question now is, what does it take to not kill a person? Let's do it that way. Not kill a person with electricity. For the human body, it is not the voltage that matters. The voltage does not matter. What matters is the current. The voltage is the height from which something drops. The current is how fast it moves. And the speed at which it moves is going to determine how much damage it does. Too much current will well, will reboot the system, but will also cause, okay, the following is a little grotesque, just to warn you. When you have current that produces heat, and that heat will, well, cook your butt from the inside. I once walked down the street and saw a squirrel on the street that had probably gotten into a transformer. Well, it's obviously not alive. And the only way I could tell is how it died was the fact that, well, one, its hair was sticking up like you can see on TV. But the ends of the hairs were charred, meaning that the exit point for the electricity was charred. If you cut that poor squirrel open, it would probably be pretty burnt on the inside, even though it looked almost completely natural on the outside, except for the ends of the hairs. And that's what happens to the human body when you put too much electricity through it. Okay, sorry for that grotesqueness, but it's the current that matters, not the voltage. Kind of like you can be hit by a piece of sand that's going really fast, and it'll sting a little, but it's not going to kill you. If I throw a boulder at you very slowly, it's probably going to kill you. So it's a measure of the volume that passes through per second, and not how quickly, and not the height from which it dropped. So a grain of sand from high voltage won't do a whole lot, but a boulder at low voltage will, because it'll have effectively high current. So it's the current that matters. Maybe that's not the best explanation, but hopefully that gives you a little bit of a picture. So now let's use Ohm's law. How much voltage can I have if my body's resistance is 100,000 ohms, which is what it is on a dry day? So on a dry day, what will it take in terms of voltage to kill me? Wow, this actually did get very dark very quickly. Okay. So let's do the math. Hopefully you paused it and done the calculation, and now you're finished. Voltage equals current times resistance. Therefore, current equals voltage divided by resistance. Oops, I didn't do that. I have the current. So my voltage that I'm solving for, even I have to go back to step one sometimes, equals my maximum allowed current is 7 amps, or 0.07 amps, 70 milliamps, times 1 times 10 to the 5th. By the way, this is 7 times 10 to the minus 2. And that gives me a voltage of 7 times 10 to the 3 volts, which if you run it just to 7,000 volt, that's fine. I only changed this to this so that it makes the math easier. Because 10 to the minus 2 times 10 to the minus 5 is 5 plus a negative 2, which is 3. All right, so 7,000 volts, which is a lot of volts. On a rainy day, your resistance can go from 100,000 to 1,000. So it makes it a lot easier to be zapped in water than it is on a dry day. Ground. Now, most modern outlets have 3 holes. The third one is the ground. The reason why we like to ground our electronics is because if you do not ground your electronics, charge can build up on the electronic. So let's say you have a lamp that's not properly grounded. Well, charges can build up on the outside of that lamp. And then when you go to turn the lamp on or off, zap. It turns you on or off. Off usually. So that's why we like to ground things. All right, AC versus DC. Thankfully, this class is taught in the 80s because everyone would be like, but AC, DC is the same. Okay, not music. So there are 2 types of current, AC and DC. AC stands for alternating current. DC stands for direct current. even though we mostly use alternating current around the world, I'm going to talk about direct current first because it's the most straightforward to talk about. DC is direct current. That means that my current as a function of time is constant and not changing. My voltage is constant and not changing. So mathematically, it's pretty straightforward. That's all there is for direct current. By the way, the only source of electricity that produces direct current is solar. That's why when you have a solar panel, you have to tie it into a device that changes your direct current to alternating current, because most devices are set for alternating current, not direct current, and it would pretty much mess up everything. Many devices need direct current instead of alternating current, and so what happens is you have a converter that converts alternating current to direct current using that big prong thing at the end of your power cord, the big box thingy that has the rock that you plug into. So you have your lamp in the shape of a mushroom. And it has a power cord. And let's say for this was an electronic device that needed direct current, it would have that big box thing with the prongs at the end. Sorry, the big giant box thing with prongs in it that you plug into it. This is the converter from AC to DC. So laptops need it, for example. So most electricity we get from the wall and gets produced is alternating current. Now we learn why we produce alternating current and why that's easier a little bit later today and as well next week. This means that my current alternates, it averages 0, and goes to some maximum and some minimum, and alternates between that maximum and minimum over some given frequency. In the United States, it's 60 times per second. Elsewhere, it's faster than that. It turns out 60 is not the ideal rate, but we started doing that 100 years ago, and it just kind of got grandfathered in, and we never bothered to change it. If you were creating the electric grid today, you would not want to use 60. You would want to use probably 120 or 180 or 240 or something like that. So, how do charges move in alternating current? In direct current, the charges just stream like a river of charge. And we probably picture that when we think of electricity. We think of this river of charge flowing into your house, flowing through your devices. But it turns out it doesn't actually work that way because of alternating current. For alternating current, what happens is we have positive current, which means it flows this way. By the way, currents can be negative. And then it stops. And then it flows back. And then it stops. And then it flows forward and backwards and forward and backwards. It's more like the waves on the ocean going in and out than anything else. And so when you pay your electric company, you're not buying electrons, you're buying the energy to move the electrons back and forth. So you are in fact paying for energy and not for charge. They're not charging you for charge. The charges are free. It's just the energy that you're charged for. That was confusing. So what happens is, though, not all the charges move the same way. They actually move kind of randomly. Now, if it was perfectly random, there'd be no current, because you'd have as much charge moving this way, as that way, this way, and this way, and so when you add it all together, it would be 0. Because current doesn't have a direction, but it does have a sign. But if, say, 10% of them move this way, and the rest of them move randomly, then I have a current going this way. And the higher the percentage of charges moving that way, the bigger the current. If all the charges move this way, we have an insanely high current because, even 1 gram of metal has a lot of charge, a lot of electrons, a huge amount of charge. We're talking 10 to the 7th coulombs of charge. So, And if that moved in 1 second, all right, and it moves close to the speed of light, so yeah, you're talking 10 to the 15th amps, a quadrillion amps. So clearly that doesn't happen. So you're 1 trillionth. If you have 1,000 amps, you're talking 1 trillionth of your electrons are moving in one direction, and the rest of them are not. So, but when you apply an electric field that deflects the electrons in a specific direction, so they kind of go a little bit more and go that way than the other way, and that's how you create a current. All right. So I covered this. You can read the page. Power. We saw before that power is energy per time, which is work over time, and that energy is power times time. Same is going to still be true for circuits that the amount of energy you have to buy from the power company is equal to the power you use times the time. So if your light bulb uses 60 watts times an hour, that's 60 watt hours at 0.06 kilowatt hours, which is going to be about 1 cent. But power also equals current times voltage. Current times voltage. So suppose our 60 watt light bulb had was attached to a 120 volt line, which is the typical voltage in your household. There's 120 volts and 220 volts. You use 220 volts for large appliances such as the refrigerator and the stove. But most of the wall outlets are for 120 volts. So suppose you have a 120 volt line, put a light bulb on from 60 watts. What's the current going through that particular light bulb? And I'll give you a little bit of time to work on this while I erase the board from the last question. All right, hopefully you are done. Power equals current times voltage. Remember, I is for current. We're looking for the current. Sometimes it's good to solve for the variable you want first and then put in numbers. So that's what I've done here. So this is 120 watts divided by, 60 watts. You can tell I'm on vacation right now. Sort of. 120 volts, 0.5 amps. Now, most households will run about 20 to 30 amps at a minimum for the entire house. All right. Now, here's a two-part. So a lot of times in this class, I gave you level 1 questions. This is a level 1 question. This one's a level 2 question because it's a two-parter. And the two parts are pretty straightforward. So imagine you have, I'll erase this part for now. You have a resistor with a resistance of 100 ohms. And you put it on a 120 volt source. And you leave this on for 3 hours. How much energy will you consume? Now remember, to get joules, you take power times time in seconds. To get watt hours, you take power times time in hours. So that's the difference. So I give you a helpful hint about the first step, and then you can do the second step. So go ahead and do those 2 steps. And if you're still unsure, look at the note. Find the current, because we need the current. Use Ohm's Law. Ohm's Law. All right, step 1. Voltage equals current times resistance. Therefore, current equals voltage divided by resistance equals, even I have to look to remember. My memory's not that good. But this is our symbol for ohms. You can use that, or you can just write out ohm. That's fine. 1.2 amps. All right. Now I stick that into this equation up here. Actually, this is a three-step problem. Sorry, you're probably wondering, where do we get the energy? So we now put it into the power equation. And get my power. Now the third step. I'll give you a moment to do the third step. Find power equals energy times time. Or sorry, energy divided by time. All right, so that means that energy equals power times time, which equals 144 watts times 3 hours. Which is 432 watt hours. Consider pretty good there. All right, hopefully that makes a little bit of sense. And that's about as difficult as I can make it until I get to complex circuits. So without drawing any circuit for you, that's as tough as it gets. That is a level 2 problem, even though it's got 3 steps. I'd still call that a level 2. It might be a little bit tougher than level 2, but it's a level 2. I don't think that one's so bad. Sometimes you just got to reason through it and do it one step at a time. Now those are the kind of problems you'll do more like the problems you'll do in real life as opposed to the first problem you use, not so much. All right, at this point we are done with part 1 and we will move on to part 2, which we will talk about the different types of circuits and then go to transformers. All that meets the eye